Integrated Math 3, this is the day 1 and 2 lesson, the very first lesson of the course, and this is on statistical inference. So the mean is the statistics name for an average. So for example, if you take the following set of numbers and you want the average of them, to find the mean you add the numbers and divide by the number of values, by how many values you have. This is represented by the equation mu, that's the Greek letter mu, simply means the symbol for a mean or an average. You add up all the numbers on top, as many as you have, and you divide by how many of those numbers you have, where mu is the mean. So that's how you would do that, and you come up with an average of 6.7. So you notice that the average does not have to be one of the numbers in the set. It's kind of in between some of the numbers in the set in this case. The mean value is 6.7. Our first unit is statistical inferences. Statistical inferences are conclusions we can draw from examining statistics. What are statistics really? Statistics are when you can't know something with certainty, you use probabilities. For example, you can't know for certain when you flip a coin whether it's going to come up heads or tails the next time you flip it. But what you can know is if you flip a coin 1,000 times, it's going to come up to be very close to 500 heads and 500 tails. Not necessarily exactly 500, but very close to that. You can know with almost certainty that it's not going to come up to be 1,000 heads and 0 tails. And that's just the way that probabilities work. So statistics are the study of probabilities, which is where you can't study every item or know every outcome. You just have to take a bunch of them together and say what generally is going to be the outcome from all of these different incidences put together. We will explore normal distributions by collecting empirical data. Empirical means experimental data. And that's a normal distribution. So the most common, if you take a lot of data, the most common data will fall in the middle, the ones that appear the most, and it forms what's called, sometimes called a bell curve, but formally it's called a normal distribution. Those numbers inside is what we're going to talk about in this class, in this particular lesson. So the mode is the value that appears the most times. So if you look at that same set of numbers, you see that 7 appears 4 times. That's more than any other number. And so that is the mode of this data set. The value 7 appears 4 times. This is the greatest number of times, so 7 is the mode. If there's more than one mode, then the set is said to be bimodal. That's if there's 2 modes. There could be 3 or 4, but usually not. The set below, which is different than the one above, is bimodal. So you have 4 3s and 4 7s. Those are the 2 that appear the most times. So that's said to be bimodal. The median is the value that appears at the center of the set. Half of the values fall below the median and half fall above the median. So if we have a set of 5 numbers, 5, 5, 6, and 7, the number 6 is the median because half the values are below and half are above. You have 2 numbers to the right of 6 and 2 numbers to the left of 6. When you have an odd number of numbers, in this case 5, your median is going to be one of the numbers in the set. In this set, 2 values are in the middle, 6 values below and 6 above. In this case, you have 14 numbers. That's an even number. So what you're going to do is have 2 numbers that are in the middle. So you do see that there's 6 numbers to the left of that red box and 6 numbers to the right of that red box. So what is the median in this case? Well, what you do is you simply take those 2 numbers in the box, the 6 and the 7, you add them together and divide by 2. You take the average of just those 2 numbers. And so 6 plus 7 divided by 2 is 6.5. So half the values are above 6.5. You'd have 7 values above 6.5 and 7 values below 6.5. So 6.5 is the median. There are 2 types of variables, categorical and quantitative. A categorical variable takes category or label values and places an individual into one of several groups. Smoking is a categorical variable with two groups, since each participant can be categorized as either a smoker or a non-smoker. Gender and race are two other categorical variables. Quantitative variables take numerical values and represent some kind of measurement. The age is an example of a quantitative variable because it can take on multiple numerical values. Weight and height are also examples of quantitative variables. So here's a little comparison of the two. On the left you have quantitative or numerical variables. So that would be, for this dog, for example, would be how many legs it has, 4. If it has brothers and sisters, how many? Its weight can be expressed as a number. Its height can be expressed as a number. Discrete means that you go from one integer to the next. So let's say the dog somehow had lost a leg. It would have 3 legs. If it didn't lose a leg, it has 4 legs. There's no way you can say it has 3.5 legs. It has either 3 or 4. The number of brothers or sisters that you have, it's an integer value. It's either 1, 2, 3, 4. It can't be 1.5, 2 3/4, or anything like that. Then continuous down at the bottom are things that can take on any value, such as the weight. Weight could be any number you want to assign, including decimal numbers. Same with height. Qualitative is things like that aren't numeric. So the color of the hair, is it brown or black? Is it long? Does the dog have lots of energy? Now sometimes you can assign numbers to those, but generally speaking those would be qualitative variables. And they're also called categorical variables. A histogram displays data that is grouped into buckets or bins. We generally use the word bin in this class. A teacher might want to create bins with intervals of 2 points in order to assign grades for a quiz, then examine the number of students at each grade level. A histogram provides a visual way to see the grades of the students. Histograms display quantitative data, so the horizontal bottom axis contains numbers. So you see on the bottom it's 2, 4, 6, 8, 10. There are numbers down on the bottom as well as on the axis going up. A bar graph or bar chart displays categorical data. Categorical data is non-numeric, such as fruits and vegetables listed on the bar graph below. So notice that the horizontal axis on the bottom there has types of fruits and vegetables. It does not have numbers. So those are categories. A dot plot uses a dot to count the number of units in each category. Dot plots can be used in place of histograms or bar graphs. So instead of having to put numbers over on the side on the vertical axis, you can just put a number of dots and then reference how much each dot means. Does it mean 1 box of popcorn or 100 boxes of popcorn or what have you? You can assign what a dot represents. Precision is how closely grouped the measurements are to one another. Precision is determined by a measure called standard deviation, and that funny symbol is a Greek letter sigma. It's lowercase sigma, the Greek letter for S, and that's abbreviated simply as SD for standard deviation. Standard deviation gives a number value for how spread out your measurements are. And there's the formula, and we'll learn how to use that formula and apply it to some numbers here in just a minute. Example, find the mean, average, and standard deviation of the following sets of numbers. So set 1 is 19, 20, and 21. Set 2 is 10, 20, and 30. So let's find the average of those first. The average is, for set 1, is 19 plus 20 plus 21 divided by 3, because there's 3 numbers, and that gives you 20. For set 2, it's 10 plus 20 plus 30 divided by 3. That also gives you an average of 20. Both sets have the same average, 20, however the values in set 2 are more spread out. And the reason you might want to know this is you want to be able to predict something. If you had to guess what the next value in set 1 would be if another value were added, you'd say, well, it's either going to be 19, 20, or 21, or something in between those maybe. So you're pretty confident it's going to be 19, somewhere between 19 and 21, which is a difference of 2. But in set 2, if you were asked to predict what's the next value going to be, well, boy, it's going to be somewhere between 10 and 30. That's a range of 20 numbers. So it could be 11, it could be 23, it could be 17, it could be 29. You just don't really know. You can't really predict where that next value is going to be. So to find the standard deviation, you make a table like this. You don't have to draw a bunch of lines. Just go ahead and put them in 4 columns. List the data values. That's in the first column, so that's the numbers. So we're taking the standard deviation of set 1 from the previous slide. List the mean values. So the mean was 20. You put that on all of the lines. Then you subtract the mean value from each data value. So 19 minus 20 is -1. 20 minus 20 is 0. 21 minus 20 is 1. So that's called the deviation. Finally, you square the differences and sum them. So you take -1 squared equals 1, 0 squared equals 0, and 1 squared also equals 1. You add those up and you have a sigma. Now this is also the Greek letter sigma, but it's the capital letter of 2. So that's the sum of the deviations, that number 2 down there at the bottom. And the number of values that you have is over there on the left on the bottom. That's n equals 3. So now we're ready to go ahead and use the standard deviation equation shown right there. So we know the sigma deviation squared, that's the 2 down there in the bottom right. The n minus 1, the n is the 3. So we're going to go ahead and plug in those numbers. Actually, first we're going to go ahead and do the other set 2. So again, list the values 10, 20, 30. The average was again 20. Subtract 20 minus 10 is, 10 minus 20 is -10. 20 minus 20 is 0, and 30 minus 20 is +10. Then you square those numbers. -10 squared is 100, 0 squared is 0, and 10 squared is 100. You add up the deviation squared, 100 plus 0 plus 100, and you get your sigma deviation squared of 200. The number of values we're dealing with is still 3. And there's the formula. So we're going to plug both of those into the formula to see what the standard deviation is. So for set 1, our sigma deviation squared was 2. N is 3, so 3 minus 1 is also 2. 2 divided by 2 is 1, and the square root of 1 is 1. So that's what you see there. For the set on the right, we had 200 for our sigma deviation squared. N is 3, so 3 minus 1 again is 2. So 200 divided by 2 is 100, and the square root of 100 is 10. The higher standard deviation of set 2 indicates that the data in this set are more spread out than the data in set 1. 68% of the values will fall within 1 standard deviation of the mean. That means 1 standard deviation to the right on the upper side and 1 standard deviation to the left on the lower side. This small data set is not enough to see, not enough data points to see that here. So what does standard deviation really mean? A normal distribution, also known as a bell curve, has values evenly distributed among the mean, among the average. So let's take a look at that curve there. In the pink is 1 standard deviation. Mu is the mean. That's right in the middle. That's right below the highest point on that curve. To the right you have 34.13%, and to the left you have 34.13%. That pink area represents 1 standard deviation to the right and 1 standard deviation to the left. And if you add those 34s together, you get 68.26, but we usually just call it 68% just to keep it simple. Now what about 2 standard deviations? That would be mu plus 2 sigma. That would be the blue area on the right and the blue area on the left. So if you added all those numbers up in the pink and the blue together, 13.59 and the 34.13, and then you double that, you get about 95%. So 95% of all values fall within 2 standard deviations of the mean. And if you go all the way out to 3 standard deviations, you have a number that's well over 99%. It's practically everything, 99.5%. fall within 3 standard deviations. You can see that virtually the entire curve is either underneath the pink, the blue, or the green area. Not quite all of it, but pretty close to all of it. So that would be 3 standard deviations, plus or minus 3 standard deviations of the mean. So on a normal distribution, about 68% of the values will fall within 1 standard deviation of the mean in either direction. The pink area on the distribution to the right represents plus or minus 1 standard deviation from the mean. The pink and blue combined are 2 standard deviations from the mean. This captures 95% of the values. The pink, blue, and green combined are 3 standard deviations from the mean. This captures 99.5% of the values. So let's actually take a look at some numbers here. And you can see they're kind of normally distributed. It's not a perfect normal distribution, but you almost never get a perfect normal distribution in real life. So it kind of looks like a bell curve, but it's a little bit lopsided. Okay, so we're going to see how it works here. So the following shows the scores on a 12-question quiz. So you had 1 student get 11 out of 12, you had 3 students get 10 out of 12, 4 get 9 out of 12, and so forth. The mean and standard deviation are, so I've already computed those. The mean is 7.6 if you averaged all those 22 numbers. And the standard deviation, if you did it just the way we did it on the previous slides, would be 2.1. So what that means is that 68% of the value should fall between plus and minus 2.1 of 7.6. So let's go ahead and test that out. So this means that about 68% of the value should fall between 7.6 plus 2.1, that would equal 9.7, and 7.6 minus 2.1, that would be 5.5. And what you see in that red bracket over there on the right, that's those two numbers. On the low side, on the left side, it's 5.5, 5.5, and on the right side, it's 9.7. And so now we look at the numbers that are inside of that bracket. We actually see 14 of the 22 values, or 64% of the values, fall within plus or minus 1 standard deviation. So you have 2 6s, 3 7s, 5 8s, and 4 9s. That's 14 numbers out of the 22. That's 64%. The discrepancy from 68% is due to the fact that the data does not form a perfect normal distribution. And also, it's kind of a small number of data points. It's 22. That's not bad, but if you had 200 or 1,000 data points, it would start to come really, really close to 68%. Okay, so that ends this lesson. Standard deviations may be the most difficult part, and you're going to do one lesson on this assignment, and then you're going to do a couple more later this week to practice that a little bit more. It's just a matter of getting used to drawing that table up. And it's more time consuming than it is hard, and so we'll practice that this week, okay? So we'll see you in class.